X, Y, and Z. I was just mentioning, calling this X, Y, or Z is a matter of perspective. And if you decided that when I fill up this level 3, see I'm putting electrons in level 3. I'll use the orange, you can see it better. We normally say PX, PY, PZ, 1, 1, 1. Then PX double, PZ, Y double, PZ double. That's how I'll do it. So I would think about this, like, say if you know the electron configuration, you write it down, then you do the quantum numbers based on that. Well, if you decide you want to go first here, PX, then PZ for number 2, your number 3 will have to go here because they have to be single, Hund's rule. You can do that. Go 1, last, middle, but then you got to be consistent. Down, then last, middle. You can do that as well. Don't do that. There's no need. But the reason I tell you that is because what you're writing with quantum numbers, you're writing possible quantum numbers. They say that. What are the possible quantum numbers that you can have? And you'll see that coming up in a little bit. All right. So, if you don't understand exactly what I mean by that, it doesn't really matter. Just go in the order I told you, and you'll always get a set of quantum numbers that are correct. Okay. All right. So, that was a little formula to let you know at any value L, ML will always equal every number from every number from negative L to positive L, including 0 in that list. Every number that's from L, negative L to 0 to positive L. And you see how that worked right there. Okay, now, and the last quantum number, and we're ready to write quantum numbers. The last one is the MS, and it's the magnetic spin. And I've told you about this before. How can 2 electrons be in the same room, like in the 2s room? Well, how can they both be in that little sphere and not interfere with each other because they're both negative 1? Well, there's a, in physics, I've told you about this. If I have a negative 1 particle and another negative 1 particle, they will repel each other. However, if one of them is spinning clockwise, and how am I going to draw clockwise? I'll do it like this. One of them is spinning, and the other one is spinning counter. Wait, why did I do that? Oh no! Ha! I didn't mean to draw it there. That went okay, whatever. It went crazy. One of them is spinning. Well, this one clockwise, and this one is spinning counterclockwise. If they do that, their negative charges will not repel each other. They'll be okay. Okay, they will not act on each other. But now, for that to be true, they have to be perfectly spinning, always exactly the same speed, turning exactly right, and aligned with each other. You can't get one like, oh, now we're in trouble. Okay, so this is not 100% going to always happen. And so it also tells you that sometimes, as you see along the line, electrons don't want to be in the same room. They're like, well, sometimes you see some ions. We talked about how they'll leave one electron here, or when you fill the D's and the F's, you start to see an electron left in. So this kind of just tells you sometimes there's a better situation, like from exceptions, to move that electron to shift it over into another orbital. But we don't have to really know of that. There's a couple I've told you about, or I'll tell you about, like for example silver, but copper and chromium. But I'll get to those later on. Okay, now, so here's an easy way to remember it. If you have 2 electrons inside an orbital, okay, let's just call this the 1s orbital. For this electron, ML equals positive 1/2. For the electron coming down, ML equals negative 1/2. So this is the easiest quantum number. Every arrow going up, the spin is positive 1/2. Every arrow going down is negative 1/2. That's all you need to know for whatever reason they decided to give that value to it. All right. So here is the way you would write some quantum numbers. And I'm making a mess out of this over here. I'm not going to do all of them because, again, this is all a bonus, and you can look in your book for a little bit more detail on it, if it's in your book, hopefully. And it is in the AP book, but if you're doing this in a general or honors, well then, hey, you are really, really outgoing to be doing this. Okay, so let's start off and do an atom that's like, let's put 1, 2, 3, 4, 5, 6. Yeah, let's just do that. 1s2, 2s2, 2p2. That would be oxygen, right? 1s2, 2s. No, oxygen. Bad. No, bad. Okay, that's carbon. Let me do another one. Well, I could do carbon, or I could do nitrogen, or oxygen, or whatever. Actually, let me do. Well, first I'll do nitrogen. 1s2, 2s2, 2p2. If we said write down the possible quantum numbers for a nitrogen atom, here is what I do, and it might seem a little crazy. I like to add onto this an orbital column. So we have 1s, 1s. We have 2s, 2s. Then we have 2p, 2p. What that means is 2 electrons are in the 1s for nitrogen, 2 are in the 2s orbital, and 2 are in the 2p. So starting from the bottom left to right, the first electron going up. This is in what level, what floor of the hotel? It's in floor number 1. N is 1. Actually, for both these, this will be the first electron, second, third, fourth, fifth, sixth. 1, 2, 3, 4, 5, 6. Oh, and there should be 7. One more. Sorry. 2p3. I'm sorry about that. I told you we'll do nitrogen. Actually, there was some on the worksheet, on the notes, and I kind of abandoned them. I wonder if nitrogen was one of them. Oh, no, it was carbon. It said write possible quantum for electrons of carbon. Well, that's okay. I'll just do nitrogen instead. So I'm doing nitrogen. So nitrogen, the electron configuration 1s2, 2s2, 2p3. Okay, these first 2 electrons are in n equals 1. The second 2 are in n equals 2, the second floor, and then these other 3 are also in the level 2. What is the L value for the s electrons? Remember, no, my S looks so bad right there, and I'm just looking at it. Okay, S is 0 for L. L equals 0 for an s orbital. So L is 0 for the 1s. Anything with an s, 0, 2s, the orbital is 0, 3s, 4s, 5s, whatever. So all of the s's will be zeros. For the ones that are p's, P tells you L equals 1. 1, 1, 1. They're all in the one wing of the hotel. Now, the magnetic number. Remember, only the P's, D's, F's, and higher up, G's, I didn't show you G's, but those would be, I mean, we don't really have to worry about them as much, but they are possible. And in the same way, just by the way, there's one S, there are 3 P's, there's always 5 D's, 7 F, so that means 9 G, 11 H, and it goes on. And all the rules, these little formulas I told you will all work. You can find out how many electrons could fit in the 11H orbital system. How many electrons can be in the 11H orbitals. All right, you can figure that out if you wanted to. But okay, that's on the worksheet, and it's all bonus. All right, but anyway, back to this. So the P, let's look at the 2P electrons. The middle one would be room number 0, -1, 0, and 1. That's the order I go in, -1, 0, and 1. Okay, now for these, the S, the room number is just 0 for both of those. And then the last one, which is easy, the magnetic number for the up electron, it'll be +1/2, -1/2. Then +1/2, -1/2 for the 2s. Now these, though, will all have the same spin. +1/2, +1/2, +1/2. By the way, Hund's rule comes up in the notes again here, and let's look at what it really says. And I've told you this before when I talked about paramagnetic. Maybe I did, maybe I didn't. Within a subshell, which means within, if you want to write above that, P, D, F, etc. Not the S, but within a subshell. Each orbital is singly filled first, then double filled. Okay, so single, up, down, down, down. Then it also says electrons in a singly filled sublevel will have the same spin. So that means that, like you see here, if I singly fill that one, and that one, they will have the same spin. That just means that's Hund's rule. You don't go 1, 2, 3, up, down, up. No, you go up, up, up. They have the same spin. And we know this from magnetism that is predicted by the elements. So this is just astounding. This is amazing. I told you, for chemistry, when Schrodinger figured this out, And suddenly they didn't have the periodic chart arranged this way, but they rearranged the chart based on what he was saying. And it's like, oh my goodness, it makes sense. That's why all of these elements, these are not magnetic. And these are not magnetic, okay? And then they went in and, oh, this one is, this one isn't. And they figured it out, and they're like, wow, this is incredible. We know we figured out something. So the magnetism, predicting magnetism of elements was a big, that's one of the big, you want to say, evidences that the quantum theory is true. Okay, so maybe early on for chemistry. Okay, so that's how you do them. Now, this is nitrogen. 1s2, 2s2, 2p3. 1s2, 2s2, because it's in the 2p3 block. What if I did oxygen? It goes to 2p4. Well, then it would be 1, 2, 3, and now you have 2 in that first room. I'll just use the orange one for it. I don't really have space, do I? I guess I can't do that, but let's see, 2, 1, 0, and positive 1/2. 2,